Welcome back to the Explainer. Today, we're unpacking Section 3.2 in detail, looking at the mathematical elegance behind a true machine learning workhorse, logistic regression. We're drawing our structured insights straight from Andrei Burkhoff's The 100-Page Machine Learning book, really digging into the math, the log likelihood optimization, and exactly why this algorithm is still such a massive classification powerhouse.
So let's clear up the most common point of confusion right out of the gate, the name. If this algorithm is explicitly used for classification, meaning it categorizes data into discrete buckets, why in the world does it have the word regression in the title? Well, it's really just a historical hangover from statistics. The mathematical formulation looks incredibly similar to linear regression, but make absolutely no mistake, this is a classification algorithm through and through.
Here's our roadmap for the math today. We're hitting the classification paradox, the infinite linear problem, the sigmoid function, probabilities and predict, maximizing likelihood, and finally, beyond binary.
Part 1. The classification paradox. Regression or not?
And that leads directly into Part 2, the infinite linear problem and the limits of linear models. To really grasp logistic regression, we've got to understand the limits of the linear model it's built on. Think about a basic linear combination of features, your standard w times x plus b. That creates a continuous line shooting off from minus infinity all the way to plus infinity. But our target in binary classification is strictly discrete. It has to be a 0 or a 1. You just can't map an infinite line directly onto a binary outcome without introducing some pretty massive errors.
Which brings us to Part 3, the sigmoid function, a mathematical bridge.
To solve this infinity problem, early scientists needed a continuous mathematical function to bridge that infinite line to a simple 0 or 1 outcome. And the standard logistic function does exactly that. It's a beautifully elegant S-curve that takes any raw linear input, no matter how wildly negative or massively positive, and smoothly squishes it into a strict, bounded range right between 0 and 1.
Under the hood, this function is 1 divided by the quantity 1 plus e to the negative x. And by wrapping our linear model in this specific equation, we get a massive benefit. The output suddenly becomes interpretable as the conditional probability of the positive class. Meaning, if the model outputs 0.85, it is essentially saying, hey, I'm 85% confident this example belongs to class 1.
All right, Part 4, Probabilities and Predict, from Math to Classes.
So how do we actually go from that smooth probability to a hard definitive classification? It's easy. We just apply a decision threshold. Since our output is bound between 0 and 1, the standard default threshold is simply 0.5. Anything greater than or equal to 0.5 gets mapped to the positive class, and anything less gets mapped to the negative class. It is a wonderfully simple rule applied to some pretty complex math.
Step 5, maximizing likelihood, finding our optimal parameters.
We've got the architecture down, but how does the model actually learn the ideal W and B weights from the training data? Well, there's a stark contrast here compared to linear regression. Linear regression is all about minimizing empirical risk using squared error loss. But logistic regression evaluates success completely differently. Its goal is to maximize the likelihood. It wants to find the exact parameters that make the observed training data as probable as possible.
Okay, the maximum likelihood objective equation. I know, it looks totally intimidating at first glance with all those superscripts and subscripts, but stick with me because if we de-jargonify this, there's a brilliant piece of logic hiding right in plain sight.
It is literally just a mathematical toggle switch. Remember, our ground truth label y is strictly a 1 or a 0. So if the true label is 1, the exponent on the right side of the equation becomes 0. That turns the entire right term into a 1, leaving us strictly with the model's output. But if the true label is 0, the left side becomes 1, and we're left with exactly 1 minus the model's output. It forces the equation to evaluate the correct probability based on reality.
As for that giant pi symbol out front, that just dictates that we take the individual likelihoods for every single example in our dataset and multiply them all together. It's exactly like calculating the joint probability of a bunch of independent coin flips. You just multiply the odds.
But here is where applied computer science has to step in to save the theoretical math. If you try to multiply thousands of decimal probabilities together in a computer, the memory just gives up. You get extreme numerical underflow. The numbers are simply too microscopic. To fix this, we use the log likelihood trick.
By wrapping our function in a natural logarithm, all those complex multiplications instantly transform into simple addition. We just sum the logs. And since logarithms are strictly increasing, maximizing the log likelihood gives us the exact same optimal parameters. It is an absolute game changer of a workaround.
Finally, Part 6, Beyond Binary, Multi-Class Classification. While it's natively designed for a simple A or B choice, logistic regression scales up effortlessly. If you're dealing with multi-class problems, one option is to swap out the sigmoid function for a softmax function, which generalizes the probabilities across multiple dimensions. Alternatively, you can use a one versus rest strategy. Say you have 5 classes, you just train 5 separate binary models. When new data comes in, you test it against all 5 and simply pick the prediction that returns the highest certainty score.
I'm going to leave you with a bit of a brain teaser today. Unlike linear regression, there's actually no closed-form solution to maximize log likelihood. You literally cannot just plug the numbers into an algebraic formula and perfectly calculate the optimal W and B parameters. So, how does the machine actually pull it off? Well, it relies on numerical optimization routines, like gradient descent, to iteratively step closer and closer to the right answer. But exactly how gradient descent works its magic? Well, we'll be tackling that in another explainer. Thanks for joining, and keep looking closely at the math behind the machine.